Hello students, if you recall in the last lecture, we proved that if H is a non-empty finite subset of a group G and closure property is satisfied in H, then we proved that H is a subgroup of G. So let me quickly summarize what we proved. We said suppose G is a group, H is a subset of G, H is non-empty, and most importantly, H is finite. So given a group G, if I have a subgroup which satisfies these conditions, if I have a subset which satisfies these conditions, then if closure property is satisfied in H, then H is a subgroup of G. So we proved that if the subset is finite, then closure property is enough for it to become a subgroup. At that stage, I also called it a necessary and sufficient condition. Though actually I have proved the result in the form if P then Q. Result in this form is not called a necessary and sufficient condition. So let's look at converse. Suppose H is a subgroup of G. If H happens to be a subgroup of G, by definition H will be a group on its own and therefore automatically closure property will be satisfied in H. So though in the problem it was not asked, converse still works and therefore this result works in the form if and only if. So to summarize, we know that if H is a subset of G, H is non-empty and H is finite, the key word is finite over here, then H will be a subgroup of G if and only if closure property is satisfied in H. That means whenever I choose two elements of H, A star B should also be an element of H, where star is the binary operation given in G and therefore it's also the induced operation in H. So for a finite subset, finite non-empty subset, henceforth it will be enough to just verify the closure property, and we are going to use this to find all possible subgroups of finite groups. However, if I have to just use this, then suppose I have a group of order 6. Then I will have to look at all possible subsets of this group, all possible subsets, non-empty subsets, and the number of non-empty subsets will be 2 raised to 6 minus 1, which will be 63. So I will have 63 subsets and I'll have to check for which of those subsets closure property is satisfied. For whichever subsets the closure property is satisfied, that subset will become a subgroup. But you see, even for such a small group, the total number of non-empty subsets is large. So a lot of work is involved in finding all possible subgroups. So here we are going to use one more result that is going to be useful to us, and that is Lagrange's theorem. So I'll be proving Lagrange's theorem a little later in the course. But for the moment, let me state the theorem and tell you how it will be of use to us. So Lagrange's theorem says, if G is a finite group, the keyword again is finite here. So if the group is finite and H happens to be a subgroup of G and H is a subgroup of G, then the order of H will have to divide the order of G. So Lagrange's theorem states that if a group is finite and H is a subgroup of G, then the order of H will divide the order of G. Well, so what exactly does this result tell us and what this result does not tell us? Let's see with the help of an example. Suppose once again, I take a group of order 6. I know that the divisors of 6 are 1, 2, 3 and 6. Now notice that 4 is not a divisor of 6. So more importantly, what Lagrange's theorem tells me is that this group cannot have a subgroup of order 4. Because if this group had a subgroup of order 4, suppose it had a subgroup of order 4, then by Lagrange's theorem, order of H would divide the order of G, but 4 does not divide 6. So it's obvious that there will be no subgroup of order 4. So Lagrange's theorem tells me that subgroups of particular orders are not possible. You look at the contrapositive. Contrapositive is if order of H does not divide the order of G, then H is never going to be a subgroup of G. So essentially you look at the order of a finite group, look at the divisors, then Lagrange's theorem tells us that there is a possibility that the group will have subgroups of this order. It does not tell us, Lagrange's theorem does not tell us that there will be subgroups of orders 1, 2, 3 and 6. As I said, more importantly, it tells us that subgroups of certain orders are not possible, and that much is also a big help for us, because then I know that in this case this group cannot have a subgroup of order 4, it cannot have a subgroup of order 5 either, because 5 also does not divide 6. So it is futile to look for subgroups of orders 4 and 5 for this group. So it helps us narrow down our search for subgroups. So let's look at a very simple example. Find all subgroups of the group G equal to 1 omega omega square with respect to dot, where omega is a cube root, complex cube root of unity. We have come across this group. In fact, this was our very first example of a finite group. So you could go back to that video and recall the composition table for this. But right now, I am interested in finding all subgroups of this group. So let's look at the order of the group. Order of the group is 3. We know that the divisors of 3 are 1 and 3. So once again, to quickly recall, remember what Lagrange's theorem tells us. If the divisors of 3 are 1 and 3, Lagrange's theorem more importantly tells us that this group cannot have a subgroup of order 2. So we have to only look for possible subgroups of order 1 and order 3. So let's first look at a subgroup of order 1. I call it the subgroup because very soon you will realize that this subgroup is going to be unique. The subgroup of order 1 is, order 1 means I need to have a subset which will contain exactly one element and which will become a subgroup. Now, if you want to have a subgroup, the most important element is identity. And if you want only one element, then it will have to be set containing only identity. Recall, this is called trivial subgroup. So, subgroup of order 1 will be always the trivial subgroup, that is the subgroup containing only identity. On the other hand, look at the subgroup of order 3. Now, subgroup of order 3 will be a subset of this of order 3 which will become a subgroup. Now the only subset of order 3 where you take 3 elements is if you take the whole group, and we know that that is also a subgroup. So subgroup of order 3 is also unique, that is the whole group. This is called improper subgroup of G. So for this group I have only trivial subgroup and improper subgroup. So this is an example of a group in which we do not have any proper non-trivial subgroups. We look at a slightly more complex example. Complex in the sense, we will now look at an example where we do get proper non-trivial subgroup. So let us now find all subgroups of the group G equal to 1 minus 1, I minus I with respect to dot. Here dot denotes multiplication of complex numbers and I is the imaginary unit. This is a finite group. Look at the order. Order means number of elements in the group. Order of this group is 4. Find out the divisors of 4. The divisors of 4 are 1, 2 and 4. So again, Lagrange's theorem tells us that this group cannot have a subgroup of order 3. So we don't search for a subgroup of order 3. We will now look for subgroups of orders 1, 2 and 4. Well, it should be easy to find out what is a subgroup of order 1 and subgroup of order 4. I'll give you a moment to think about it and then we will come to subgroups of order 2. If you take subgroup of order 1, as I told you in the last example, it should be a subset which will contain only one element, and if the subset has to contain only one element, it has to have the identity and nothing else. So subgroup of order 1 is set containing identity, that is 1, and subgroup of order 4 is the whole group. This is trivial subgroup, this is improper subgroup. Now, if at all this group has any other subgroup, it will have to be a subgroup of order 2. So let us look for subgroups of order 2. So we now obtain subgroups of G of order 2. So one method is to find all possible subsets of size 2 and then see which of them become subgroups by checking whether closure property is satisfied for them. Now I do not want you all to actually list all. Okay, firstly, how many subsets will be there of size 2? We have 4 elements in the set and at any one stage we wish to choose 2 elements for our subset. So if you do the calculations, it's going to be 6 subsets. So this set has 6 subsets of size 2. If you want, you can list them: 1 minus 1, 1i, 1 minus I, then minus 1i, minus 1 minus I, and I minus I. So these are the 6 subsets of size 2. But if you look at it, straight away you can reject some of the subsets. For example, why do you think this will not become a subgroup? At a glance, quickly. This will never become a subgroup for the simple reason that it does not have the identity. So this will never be a subgroup. For the same reason, this will never be a subgroup. And this will never be a subgroup. So you can quickly reject some of these subsets. So for any such problem where you have a fair amount of subsets for which you need to verify the closure property, it's always better to think a little smartly and reject a few cases and look at only the good choices. So in this case, what I mean by good choices, Since I'm interested in subsets of size 2, which will ultimately become subgroups, I fix one element as identity and I choose my other element. Now my other element can be either -1 I or -I. So I have essentially 3 subsets. 1 -1, 1 I and 1 -I. So let's quickly verify the closure property for this. For closure property, the best method is you prepare a composition table. And notice that all entries in the body of the table are from the given set. Closure property is satisfied for this. So H1 is a subgroup of G. Here again let me quickly make a composition table. 1 I into I is I square, which is -1. Notice that this element is not in the given set. So closure property is not satisfied for H2 and therefore H2 is not a subgroup of G. You can also verify that H3 is not a subgroup of G. Please remember -I into -I will be equal to -1, not +1. So the only subgroup of G of order 2 will be 1 -1. So that's how we find subgroups of all subgroups of a finite group. We'll continue with such examples in the next lecture. Thank you.